Corona video 16, combo series and parallel circuits. At it, BHS, the Purdue of the MVL. All right, today we're going to kind of take what we've learned so far and we're going to kind of put it together. So we're still going to start with a battery. So I'll just make my battery look kind of like this. Positive here, negative here. I'm going to have it go away with some ideal 6-volt battery. I'm going to have it go away with some ideal resistanceless wires. And then we're going to go through some resistors. Let's just make them light bulbs this time. So we're going to go through a 4 ohm light bulb. And then let's go through a 7 ohm light bulb. And then we're going to go through a break. So here's the parallel portion. So we have a break, and then we're going to go through 2 light bulbs, but they're going to have different resistances. It's going to come back together, and then we're going to take it back to the battery, like that. Now, these will be a 3 ohm and a 9 ohm. Now, if this was in series, you could just add them up, and it'd be 9 plus 3 plus 7 plus 4. And so that would be pretty easy. That would be like 23 ohms. But because this is in parallel, it's not going to be so simple. So what we're going to do is we're going to start by focusing in on this part right here. So that's the part I want to focus in on first. So in the last video, we learned how to find the effective resistance for a parallel part. So we learned when there's just 2 resistors, we can do it by taking the 2 resistors, multiplying them together, and then dividing by their sum. So here we have a 9 and a 3. So we're going to end up with 27. So we get 27 twelfths. So what is the effective resistance of the parallel part? We would end up with 27 divided by 12, which is 2.25, 2 1/4. That's just the parallel part. So you add 9 and 3 together in parallel, and you get 2.25. Now we have to add that to the other parts that are in series. So if I was to redraw my circuit now, I can start to break this down smaller and smaller. So if we have our battery again, 6 volts, and we run it through a 4 ohm resistor, light bulb, and a 7 ohm resistor, light bulb, and then we break it into a 2.25 ohm light bulb. Let's just say resistor. And then we bring it back to our circuit. Now, if I ask you to find the effective resistance of this whole thing, it's very easy. You just add them up, R1 plus R2 plus R3, because it's in series. So we're going to say 4 plus 7 plus 2.25. So that'd be 11. 13.25 would be my effective resistance. So we could draw it again. We could draw it again, simplifying it, and we could just have one big resistor here. And that one big resistor would be 13.25 ohms. And we had 6 volts going into the circuit. So now we're ready to use Ohm's law in the effective resistance to figure out what the current is in the battery. So to do that, we take 6 and divide by 13.25. So we get 0.45. We'll say 0.453 is our current. So in the battery, when we want to know how much current, is flowing through it, I for current, we get 0.45. Let's just say 0.45. Now, everywhere in that circuit would be 0.45. So in the wire would be 0.45. Anything in series is going to be 0.45. If there was only one resistor, it would be 0.45. But it's not really that simple. We could kind of track back a little bit then and see that this would be 0.45, and this would be 0.45, and this would be 0.45. And if this was one resistor, it'd be 0.45. But the problem is it's actually two resistors. So this is 0.45, this is 0.45, this is 0.45. If we add those two together, they give us 0.45. But individually, they're unknown at this point. So as far as voltage goes, that's another thing we should probably focus in on. The voltage at each of these spots. You can find voltage using Ohm's law. Shocker, I know. So how would that work? Well, the 6 is going to be divided up amongst these guys. So when we're done, like this voltage plus this voltage plus this voltage would equal 6. Or we could say this voltage plus this voltage plus this voltage equals 6. But if we had them all together, it would be more than 6. We only want to take parts of it when we put it together. All right, so how are we going to Ohm's law? We're going to do it a number of times here. So we'll start here by putting in the following. 7, 4, and then remember we had an effective resistance here of 2.25. And then we can put in our current. Remember, everybody's got 0.45 for their current. Everything in series, that is. And we'll get our voltages. 0.45 times 7 is 3.15 volts. 0.45 times 4 is 1.8 volts. And 0.45 times 2.25 is 1.01. All right, so that 6 volts gets distributed amongst these. And we can kind of do a quick check on this by adding them together. 3.15 plus 1.8 plus 101, that gives us 5.96. Now, if we would have taken a more exact number, we would have got this. And so that's our check. So let's go through and we'll put in our voltages on our schematic now. So going through the 7, it takes 3.15 volts. Going through the 4 takes 1.8 volts. And going through this break right here, okay, going through the break takes 1.01 volts. So we get 1.01 and we get 1.01, basically 1. So what we can then do is we can do Ohm's law again individually for the 9 and the 3. So V equals I times R again, but this time we're going to do it for 9, and it had a voltage of 101. And then we're also going to do it for the other resistor in parallel, 3. And we're going to solve for this missing current. So we say 101, and we divide it by 9, and we get 0.11. Hardly any. And then here, we divide it by 3, and we get a bit more, 0.33. Added together gives you 0.44, which is like really close to 0.45. Okay, so we would say 0.11, it's actually 0.34, which gives us better, okay? So we'll put in 0.34 0.34 here, and 0.11 here. So let's think about the current for a second as it goes around the circuit. So initially we have a lot of current, right? So we start off with our 0.45 and we go through our first light bulb. And so it's going to glow sort of brightly. Then we're going to go through our next light bulb. It's going to glow with the same brightness, even though it has a different resistance because they're in series. And then we enter the break. And as we enter the break, it splits. And most of it goes through here. And just a trickle goes through this. See, it takes the path of least resistance. It wants to go the easiest way. And it does. So it chooses 3 over 9. And then it comes back to the battery then, just like it left. And because the wires are ideal, the current that we started with is the same as we stop with, 0.45, if you add these two things together. So the thing you want to think about in this combo circuit is you've got to kind of start and then break it down smaller and smaller and smaller. So that was the idea that I used, was trying to make the circuit get more and more convenient. So what we had to do was we started and turned it into the parallel portions, resistance, and then we had series, and then we were able to come up with the overall resistance. Using that overall resistance, we could find the current in the battery. Then we knew the current, everything in series, and we knew that it would split up. But because they didn't have the same resistances, they didn't split up equally. And most of it went through the 3, and just a little bit went through the 9. But when it came back together, we were back to 0.45 again. That's how it finishes up. So that's how you do a combo series parallel. And that's what you're going to see in the problem set. And that's what you're going to make in your lab this week. All right, so that's the end of our Corona videos. Thanks for watching.